Hello and welcome to today's webinar. We'll be just starting in just a few seconds. Okay, so my name is Dr. Tim Walmsley. I'll be talking about reducing process heat use through retrofit design of heat exchanger networks. This is a bit of a heavy topic today. It's a little bit more complicated than the other process heat ones we've done in the past, and so we'll take it slowly and hopefully we can discuss and talk about a few of the various methods of how to do this. So here's just a bit of an overview of what we're going to talk about. We'll give a bit of a brief review of what we learnt in our last webinar on process heat. Then we'll talk about how we can adjust these methods that we learned and apply it to a retrofit situation for a heat exchanger network. Then we'll look at a refinery case study, which is sort of quite a typical case study, and then we'll sum up at the end. Okay, so let's just in review, there's lots of different ways we're looking to save thermal energy. We've sort of listed a few on here. The retrofit design stuff sort of sits in the middle. It has quite a good potential for energy savings, but does require a fair amount of resources and capital and time and effort. It is a bit of a specialist field, and so it may be something for a large energy user that you look at engaging a consultant. So let's just review what we learned last time. Last time we talked about a technique called pinch analysis, which we mainly applied to a situation where a site already exists, and these are some of the main steps that we have. We have a process flow diagram. From that we try and extract and apply a mass and energy balance, try and reconcile the data. We then extract out streams or flows that need to be heated and cooled, and we assign them specific supply temperatures and target temperatures, and so that we can then construct and perform this pinch analysis and along with composite curves to get a target for how much heat recovery we can get for a specific minimum approach temperature for the network. Then we can go ahead and use that information and design a heat exchanger network to meet that target. After we've designed the network, there's usually opportunities to relax or simplify, and then we need to simulate and optimize the network using simulation of heat exchangers in order to know how it will perform under various circumstances. So just a review of how we get these composite curves and targets. We have stream data that basically consists of a target temperature, supply temperature, and a duty. And then we have an MCP, or a heat capacity flow rate, which is essentially the duty divided by the temperature change. So on the left here we've got a diagram just showing temperature versus enthalpy, and we can composite these two flows together, and so we end up with a composite of the two. We can do the same for the cold side, and we take that stream data, we can plot it on the graph here and composite the two, and we end up with curves that we can pinch together for a minimum approach temperature that is specific to an industry or a unit operation, and 10 degrees is a fairly common minimum approach temperature for a refinery. 5 degrees tends to be more of a dairy or food and beverage low temperature processes. From this we can read off certain targets. So here we've got a target for the amount of heat recovery we can recover from the process, and we also have a target for how much hot utility and cold utility that we need for this particular process. Now, one of the important aspects of these curves is the location where it pinches. Around this area we have a heavily constrained area of how streams and flows are to be matched in order to maximize and reach these targets. And you can see that at this point there's a constraint around the temperature. And so below the pinch we are usually in a surplus of heat, and above the pinch we're in a deficit of heat, meaning we need hot utility above the pinch and we need cold utility below the pinch. And so this pinch divides the problem or the situation into two distinct regions, and where one is in need of heat and one is in excess of heat. And so if we have in our network a design that is taking heat from above this pinch and using it to heat streams or flows below the pinch, we have what we call cross-pinch heat transfer, and that is an inefficiency in a network, and it's fairly easy to identify. Now, just some more review of how we can I guess draw these heat exchanger networks, because it's quite important to have a systematic method of how to draw them. Essentially there's a number of components. There's the process streams, there's the utility exchanges, there's the process exchanges. And so one of the common diagrams is what we call the grid diagram. This is an example of a grid diagram where we've got 4 heat exchangers, and on the upper side we've got hot streams, hence they're red, and they're cooling down from their supply to their target temperature, and on the lower side we have the cold streams that are going from a cold supply temperature up to some target. These are our process-to-process heat exchangers that essentially show that in the case of the first one that's pointed to, stream H1 is matched with stream C2. We also have here showing the heaters and the coolers that are required, and so these are the utility exchanges. This is just a method of how to illustrate what a heat exchanger network looks like in a very clean way. There of course are many other ways how to illustrate a heat exchanger network, but this is the one that we're going to use today. So let's look at a retrofit method and a bit of a case study to demonstrate it. There are primarily 3 reasons or objectives for wanting to do a retrofit. The first reason is we're wanting to debottleneck our process, and so this means we're essentially trying to get more throughput in the process, and sometimes the heat exchanger network or the utility supply is the limitation. And so if we're able to increase the heat recovery within the heat exchanger network, we may be able to use our existing utilities, existing steam boilers or refrigeration units, in order to get more throughput. Of course there are other bottlenecks within a process, often around the reactor or the separation units, but one of them may be, in some circumstance, the furnace or the boiler in the utility system, and therefore how much heat recovery you get. The second objective may be simply just to reduce energy. It's not necessarily to increase production or throughput, it's just to lower your specific energy. Then the third reason is there may be a modification to the process, or perhaps a feed or even a product, and so it may require different supply and target temperatures for the network, and so we're having to retrofit in order to meet these target temperatures under new conditions using the existing network, and this may require modification to the actual network by installing new heat exchangers or other possible modifications that we'll talk about. So just to give you a bit of an overview of the method we're going to apply today, to to a refinery case is we're going to look at, there's a process flow diagram. I haven't included it here, but from that we can identify and extract the stream data. We can perform pinch analysis as if it was a greenfield or a new site. Then we can use those composite curves and the concept of the pinch to identify areas within the existing network that violates the pinch. And then we can also identify what we call the network pinch that is different to the what is the process pinch or the pinch from the composite curves. Then we'll look at methods of how to evolve the network using a sequence of modifications that centers on the network pinch and how we can then move towards the target. Then number 6 is we've got to perform a simulation and a detailed economic evaluation of the network modifications in order to assess whether we should go ahead. And so we're going to focus mainly on the methodology of how to do steps 2 to 5, which is the most probably difficult steps. So I've taken an example from a refinery unit operation around one of the distillation columns, and this is essentially what the network currently looks like. It's relatively simple. You can see there we've got 3 hot streams and 2 cold streams, 3 heat exchangers with a heater and 2 coolers. The current system is recovering 18.6 megawatts with the respective hot and cold utilities to make up the remainder of the duties required. So we can extract from this the stream data and put it into a form which is useful of the supply and target temperatures, the heat capacity flow rates, the duty, as well as noting what the heat transfer coefficients are for the various fluids in the heat exchangers. From here we can do what we've done in the past of target heat recovery using the composite curve approach, and in this case we've selected a minimum approach temperature of 10 degrees. Now it's important to note that the pinch temperature, although it is singular in the sense that it's one temperature, it has a temperature that applies to the hot streams and it has a temperature that applies to the cold streams that relates to this minimum approach temperature. And so we have a hot pinch in this particular example of 159 and a cold pinch of 149 degrees, and I'll explain in just a moment of why they're significant when we look at the network again. So the target says that we should be able to achieve 27.6 megawatts without breaking or going below a minimum approach temperature of 10 degrees. So this is equivalent to a 9 megawatt increase in heat recovery, or about 50% increase in heat recovery. So the question is now, how do we do this? And I guess, should we try and get all of the 9 megawatts, or do we stop at some point and just make a relatively minor modification in order to get the majority of the benefit? So if we look at the network again, we can identify where there's cross-pinch heat transfer according to the hot pinch temperature for the hot streams and the cold pinch temperature for the cold streams. So I've drawn a green dashed line here around the network. So starting at the top here, we've got a hot pinch of 159 degrees, and so that means that stream H1 essentially is all below the pinch. Stream H2 has the green dotted line passing through the cooler, meaning that we've got part of the stream above the pinch and part of it below the pinch. And so essentially in this particular case we've got cross pinch heat transfer going on in the sense that we've got cooling above the pinch, and so that immediately is an inefficiency. Then for stream H3, you can see on heat exchanger 2, we've got again cross-pinch heat transfer occurring. It's coming into heat exchanger 2 at 171 degrees and coming out at 90 degrees, and the pinch is at 159. And so here's another example of cross-pinch heat transfer within the heat exchanger network as opposed to within a utility exchanger. Then looking below at the cold streams, stream C1 is all below the pinch, and stream C2 crosses the pinch with heat exchanger 1 having cross-pinch heat transfer within it. Now there's multiple methods of how to go from here towards a design of a retrofit heat exchanger network. I'm just going to present one of the methods, and that's called the network pinch method. The big positive with the network pinch method is it's a sequential method where you make one modification at a time, and at any point can stop and say, okay, that looks like we're getting a good amount of heat recovery with very few modifications. Whereas if you go all the way to design a network to meet the target, it often can be rather complicated and difficult to modify an existing network to get to that final point. So let's look at what is the network pinch in this particular case. The network pinch is analogous to the concept of a process pinch, except for it's more specific to the heat exchanger rather than across the entire network. So if we look at the 3 heat exchangers here, each heat exchanger has a minimum approach temperature, and we've got heat exchanger 1 at 53, heat exchanger 2 at 20, and heat exchanger 3 at 89. Now in the previous diagram we showed that heat exchanger 2 as well as heat exchanger 1 had cross-pinch heat transfer. And so what we can identify here is in fact heat exchanger 2, because it has cross-pinch heat transfer and has the lowest minimum approach temperature, we call that the network pinch. And in this particular case that network pinch is on the cold side of heat exchanger 2 with a you can see the hot stream H3 going down to 90 degrees and C1 coming in at 70, and so you can see there is the 20 degrees that we're talking about. So one of the easy, I guess, concepts to look at is what if we just simply reduce the minimum approach temperature on the network pinch, and we do this essentially by adding area or effective area. We use the term effective area because adding tube inserts for a shell and tube heat exchanger increases the U value as opposed to increasing the A value, but in essence it's all the same. So if we were to decrease our various minimum approach temperatures, we can look at that network pinch going down to 10 degrees, and we can also look at heat exchangers 1 and 3 and the impact on those 2 heat exchangers.
I don't know.
And so in this case what it means is we're going to have to add area to all 3 heat exchangers.
Yeah, if they don't have that undercoat there, they don't get it, and we'll get it from wherever we got it. But that's
sorry,
the right stuff to use. I thought I did get it from there.
There seems to be...
The other thing to think about is, do you get fractured air flow?
Sorry, there seems to be some interference on the line here. Just a moment. Okay, sorry. Back to our webinar. So what we've got here is, before we were recovering 18.64. As we reduced down to the minimum approach temperature of 10 degrees for that second heat exchanger, we were able to increase heat recovery by a little under 1 megawatt, which is equivalent to 5%. But this is still well below our target of 27.6 megawatts. So what this means is we're going to have to modify the actual structure of the network in order to get much closer or even achieve the target. There's essentially only 4 ways which we can make modifications to the network. One is we can take the existing heat exchangers and resequence them. 2, we can take the existing heat exchangers and repipe them. And I'll explain using the example of the refinery of how these are slightly different. Number 3, we can install a new heat exchanger, and number 4, we can add a flow split or a stream split where we make 2 heat exchangers in parallel. Now essentially the objective here is we need to move heat from below the pinch to above the pinch, and in order to in other words, we need to eliminate this cross-pinch heat transfer that's going on. And so keep that in mind as we look at these various examples. So resequencing of the network. An example of this for heat exchanger 3 is we try and alleviate the network pinch by making the cold fluid going into heat exchanger 2 be even colder. And therefore we open up that side of the heat exchanger in terms of its approach temperature. And so in this case we take heat exchanger 3, which is upstream of 2 on the stream C1, and we move it to be downstream of that network pinch exchanger 2, as you can see in the diagram. This change to the network brings about a greater I guess increase in heat recovery than simply increasing the area on the existing structure of the network, as we saw in lowering the delta T min. And so in this case we go from 18.64 up to 20.98 megawatts heat recovery, with the equivalent reductions in hot and cold utility use. And so in this particular case we've increased heat recovery by 13%. What this means in I guess real life is we've repiped the sequence of stream C1 and how it interacts with the network. So instead of taking C1, supplying it to 3, having the outlet then go to 2 and then out, we're now supplying it to 2 and then to 3. And so hence we use the term resequence rather than repipe. Repiping, on the other hand, is demonstrated here, where we've taken the network pinch and we've repiped it from stream C1 down to stream C2. Now the reason for that is, if we just flick back, you can see that you can see that if we do that, we're able to increase the duty on exchanger 3 in particular, and we're also able to slightly increase the duty across 1 and 2. And so in the end we come up with a repipe network that is able to increase our heat recovery. but there is a bit of a caution that in some cases when you do repiping or even resequencing, that may impact on whether you need cold utility on a stream. And so in this particular case, if we repipe the network, it incurs the penalty of having to install a new utility exchanger on stream H3. And so this isn't necessarily a very good option. It happens to be that it increases heat recovery by very much the same amount as, or very similar to the previous example of resequencing the network. Now, another option is to add a heat exchanger. Now, one of the options, this particular option is we want to be able to, again, move heat from below the pinch to above the pinch. And so in this particular case, what we're attempting to do is we're taking heat at the 159 degrees on stream H1 and we're matching it with stream C2, as you can see in exchanger 4. What this does is it shifts the temperature ranges that exchanger 1 is operating at. And so in essence, we're shifting H1, and therefore we're ensuring that we've got heat going from below the pinch to above the pinch. And then likewise, what we can see with the network pinch exchanger, exchanger 2, is we're now supplying that heat exchanger at 159 degrees, which is the pinch temperature. And so by adding the heat exchanger number 4, we've been able to alleviate some of or a fair amount of the cross-pinch heat transfer that's occurring within the network. Now, what's interesting about this is as we've added heat exchanger 4, you'll notice that this now is got a minimum approach temperature of 10 degrees. And also, heat exchanger 1 has a minimum approach temperature of 10 degrees. And so these two heat exchangers, which sit above and below the pinch, are now very much constraining the network, and these become the network pinches that relate to the network itself. So adding this heat exchanger has had a dramatic effect on the heat recovery possible. We've gone from 18.64 all the way up to 25.38. Remember, our target was 27, and so we've gone a long way towards getting that target by adding one heat exchanger. And we've done that by identifying where the network pinches in the network and a method of how to ensure that we're getting heat from below the pinch to go above the pinch. So we can also look at what if we want to go further and we decide that we want to keep this heat exchanger 4 and let's add an additional heat exchanger to get even closer towards our target. Now, of course, with all of these options, all of these modifications, there's multiple options of how heat exchangers can be added or which heat exchangers can be resequenced and which in the network pinch to be repiped. We're just sort of exploring some of the options, but of course there's multiple options that you'd have to consider if you were applying this in your process. Okay, so in this case we're going to put a heat exchanger between the two network pinches of 1 and 4 to essentially help divide the problem further and get heat that is above the pinch, which is stream H2, and put that into stream C2. And so essentially we're again doing the same concept of shifting heat in heat exchanger 1 to be further up in temperature because we have lots of temperature on H3, while between the heat exchanger 5 and heat exchanger 4, you can see that it's 149 degrees on C2 and it's going in at 159 on exchanger 4 for H1, and so essentially we've got those two being around the network pinch again at a delta T of 10 degrees. And so after making this change, we're increasing our heat recovery by about 1.6 megawatts or 6%, and we have the subsequent reductions in the utilities. Now we can go further and look at adding a stream split where we recognize that if we're able to split stream C2 into two and supply a colder temperature to both 1 and 5, then we're able to extract even more heat out of those two streams and therefore increase our overall heat recovery. Now in this particular instance, what we've got is heat exchangers 1, 5 and also 4 all have the minimum approach temperature of 10 degrees. Sorry, my box is slightly misdrawn. But all three of those heat exchangers now have a minimum approach temperature of 10 degrees. And if we look at what we've done 3 modifications. We've now reached the target of 27.6 degrees, 27.6 megawatts for the network. Now, this is very useful information to know what the target is and to know that after we've made these modifications, we actually cannot improve upon what we've got right now without going to a lower minimum approach temperature. And so it's a very logical place to stop, and there's no point in searching further. So to recap, what we've done is we've looked at a sequence of modifications where we've added heat exchanger 4 and we've identified the location where to add it because of the network pinch. Then we've shifted where the network pinch is to heat exchanger 4 that was added, and we've identified a place to put another heat exchanger, which is heat exchanger 5. Then after adding 5, we tried to put in a stream split, and we identified a location for the stream split in order to try and increase the heat recovery from heat exchangers 5 and 1 and essentially put them into parallel. And so this was a sequence of modifications that we would need to make to the existing network in order to reach the target that we set using pinch analysis. Now the question then arises is, so which of these modifications should be implemented? Should we just implement modification 1, or should we do 1 and 2, or 1, 2 and 3? This is a question of essentially economics as well as performance of the network. There are other considerations to make as you consider which modifications to make. One of them is around, can you get some accurate cost estimates for the retrofit of the heat exchanger network? And so as much as you may do some estimates around the various modifications, but it is difficult to say whether these are accurate or not. And so often it is a wise move to do sort of 1 or 2 modifications and look at a rather more detailed costing of it rather than a loose costing. In some cases it may be difficult to add area, and so especially for a shell and tube heat exchanger. So this is where you can consider heat transfer enhancement such as tube inserts in order to increase the overall heat transfer coefficient and therefore increase the duty of the heat exchanger. There also may be a pressure drop or a head limitation for the pump, or it may be that you just have to take into account that you're pumping more fluid around or against the greater head, and so therefore incurs a requirement for power and electricity use. These are some just additional considerations. Some more that you may want to consider is space. In a lot of plants, the heat exchangers or the processes are very tightly and compactly fitted together within a building, and so there may not be space for a large heat exchanger, or and so hence repiping and the resequencing would be the preferred methods to increase heat recovery. Because of course we can still do that for this particular network, but it would just be a lot lower increase in heat recovery. So to draw on some conclusions that we can draw from the presentation, retrofits are a lot more difficult than greenfield design, and the method that has to be applied is a little bit more trial and error focused rather than a simple from start to finish a rather defined method. And this trial and error does require a lot of time and effort in order to figure out whether a modification is beneficial or not. So this results in having to explore a lot of modifications and potentially a lot of different branches on in different sequences to try and figure out which is the best retrofit pathway in order to take towards an improved network. I highly recommend getting a specialist and also automated software to help with this process. This presentation is more about to give you a bit of background on how a retrofit can be done and how one of the methods to do it, and to give you some tools around and the questions that you may ask a specialist if they were to come in to your plant and analyze your network and propose some retrofit designs. And particularly for very large problems, a simple or a method as the one we've presented today is much more difficult to apply. And so you need some automated techniques and automated software in order to do that. So where to from here for the next webinars? We have the final 2 webinars of the year. We've got Dr. James Neal talking about energy metering and monitoring in 2 weeks' time on the 30th of November. And then we've got energy benchmarks and targets on the 14th of December by Dr. Martin Atkins. Do register, you click on the link, and also if you have any questions, you need some advice and support, contact your ECA account manager, and we look forward to seeing you in the future webinars. I'll stay online for answering any questions that you may have and try and give you some guidance. Thank you for listening and have a good day.